For the last year or so, Shakid, Fleur and I have been working on using KLEE with large Rust programs. In this talk, I'm not going to be able to describe all the problems and solutions we ran into in detail. There's a link on most of the slides that you can follow to find more written detail, and of course there's the source code. The Rust is interesting because it fundamentally improves the security of the programs that are written in Rust, in particular by improving memory and thread safety through an innovative type system, the language design, and API design. And because of this focus on security, I think there's a lot of interest in the language, a lot of momentum, and it has a significant chance of becoming one of the major languages in which the world's infrastructure is built. For this talk, you need to know two things about Rust. The first is that Rust programs may be quite small in terms of the source code, but they are actually quite large when you look at the code that's executing, because Rust programs use quite a lot of libraries. There's a large, rich standard library, and there's a lot of open source libraries which are also used with Rust. And so a Rust program can easily be using 50 or 100 different libraries. So Rust programs get quite large quite easily. The other thing to know is that Rust is compiled in a number of stages, and the main stages are the mid-level and intermediate representation that's Rust specific, and of course the LLVM IR, and then it compiles to x86. And people have been writing verification tools that hook into either the Mir level or the LLVM level. And for this talk, of course, we're interested in the LLVM level because that's what KLEE uses. So to use KLEE with Rust, we started off by taking KLEE's C API and creating an idiomatic Rust API that uses Rust features appropriately. For example, we use traits to make the KLEE Symbolic type safe. And so the rest of the API is more or less what you'd expect if you're a Rust programmer and you're familiar with KLEE. Now, on top of that low-level API, we also created a high-level API. And our goal here was that we wanted to have a choice of verification techniques we can use. In particular, we wanted to be able to use fuzzing, or to be able to use tools like symbolic execution, bounded model checking, and so on. We wanted to be able to create a single test harness which can be used for all of these different techniques, so that any investment you put into developing a good harness to use with KLEE, you can also use that harness with other verification tools or with a fuzzer. So we're trying to lower the incremental cost of using more advanced verification techniques. Now, the API we're using is actually the PropTest API, which is a Rust library for property-based testing. And it's heavily influenced by Python's hypothesis library, which some of you at Imperial might be familiar with. PropTest has two main parts to it. The first is a macro which you wrap around the code you want to check, and that expands out into a suitable test harness, which is going to do different things depending on whether you're using fuzzing or using KLEE. And the other part of PropTest is a domain-specific language for creating structured symbolic values. So you can create values in a range, you can create ASCII strings of a certain length, but you can also create arrays of values in a range, tuples of a range and strings, and in fact you can kind of build arbitrarily complex structures using this EDSL. So let me give you a quick demonstration of what that looks like. Here we have an overly simplistic example which uses PropTest on the outside to build a test harness around the code, and then on the inside it's using this embedded domain-specific language to create symbolic values. And what this code is doing is checking that the product of two numbers in the range 1 to 1,000 is in the range 1 to 1,000,000. So we found that both APIs work well for small standalone programs. There are some features that KLEE did not support that we were finding in Rust programs, but they didn't occur too often as long as we were focused on a single module, but unfortunately, Rust programs, especially interesting Rust programs that we're interested in being able to use KLEE with, don't use just a single library, a single module. They instead use 50 to 100 modules. And so here we started to run into a problem that even if the code that we're directly working on does not use our difficult feature that KLEE doesn't support, one of the libraries that our code depends on almost certainly does, because there are so many libraries, there's a high chance that one of them is going to cause problems. And so we set about making a list of different kinds of features that cause problems for KLEE. And these were features of the language in the compiler, in particular where the Rust compiler generated instructions which Clang does not usually generate. Problems of the runtime library, problems of the build system around interoperation between C and Rust. There were features in the standard library. These tend to be really quite complex, of course. And in particular, we couldn't even access command line arguments without support for a particular kind of initializer, which unfortunately KLEE did not support. And when we looked at these open source crates that people often use with Rust, we found that a bunch of the most important ones had hand vectorized code that used the processor-specific vector intrinsic functions. And so we set about trying to add support for these different features. And we started off by trying to add support directly into KLEE. Now, this worked pretty well, but after a while, we realized it would be better to write a preprocessor that took the output of the Rust compiler and fixed problems in the code before we invoked KLEE. We prefer this approach because there's a potential that we can use that preprocessor with other LLVM-based verification tools. We also wrote libraries to fill gaps in KLEE's libc support and also an emulation library that our preprocessor can use to replace vector intrinsic operations with calls into our emulation library. And of course, we sometimes had to use Rust compiler flags to make sure that everything is being built via LLVM. And so we now have support for almost all the problematic features that we've been seeing. The main ones that aren't supported at the moment are concurrency and inline assembly code. And the rest we solved using one of those 4 techniques that I mentioned earlier. So once we were able to take most Rust programs and feed them into KLEE, we were able to actually start using KLEE in some code. Now, we haven't been at this very long because there were quite a lot of features we had to add support for. But let me give you a bit of a flavor of what we've been doing. So we tried some small libraries like base64 encoding. And for those, they have a decode and encode pair of functions. And so there's an obvious way of using those as oracles for each other. And so we were able to show that those libraries actually are correct. We then moved on to a Rust re-implementation of the GNU core utils library. So these are intended to be a drop-in replacement for the GNU core utils that KLEE has been used with many times in the past. There's about 100 applications. And what we found so far is we found a few minor bugs involving UTF-8 handling. We haven't done a thorough study the way that KLEE has been used with the GNU core utils in the past yet, but we may get to that later. And then we've been tackling two things which are of much more interest to Google. The first is that there's been an effort to write Linux kernel device drivers in Rust. And we ran into some challenges here. The first is we don't really want to use KLEE on the entire Linux kernel. We want to focus on the Rust bits of code. And so what we did was we created a mock layer for the bits of the Linux kernel that the Rust code calls out into. And then another challenge we hit was that the KLEE runtime libraries were compiled with different flags from the Linux kernel. And so we had to figure out a way to fix that. And we're currently figuring out the best way to write good test harnesses for that code. And then we've recently started looking at KeyStore, which manages the private keys in Android. We haven't got very far with that yet, though. Okay, to sum up, we've created two APIs to access KLEE from within Rust. One is a direct implementation or direct layer on top of the KLEE API, and one is a fuzzing layer, is more like a fuzzer, so we can use a fuzzer or KLEE interchangeably. We can support most Rust features, not quite all of them yet, and we've tried to add support in a very reusable way that we can maybe reuse with other tools. And just recently, we've started using KLEE on larger code bases, but we haven't got a lot of experience of that just yet. So thank you very much for your attention, and I'd be happy to answer any questions you may have.